All right, so today we're going to continue with what we left off last week. The only thing we didn't do was the mixed integer programming example. And the one that we're going to be doing today is about the travel salesman problem. By now, you should all be familiar with it, I believe. Everybody here is taking discrete optimization, right? Okay, you know how this problem works, everybody? Just gonna go over it just to make sure. So we have a set of cities represented here in the drawing with dots. And we define what is this? A binary variable, xij, meaning, it's gonna take the value of 1 if in the route that you're gonna set, the links I and j are gonna be linked. The cities I and j are gonna be linked, yeah. So we have to decide the shortest route to go across all of the cities. That's the objective here. So we have a component of cost here, Cij, which is the cost of going from I to j, which can be time, distance, or an actual cost. Like it can be money as well. And this is a particular formulation. You may see in some other place some other formulation, and that's okay as well. But we're going to be doing the example with this one. Notice here that, I don't know if you can see, the summation here is over I and then over j, but I have to skip the j's that are equal to the I, and the same here. And in particular in this one, the subterm elimination constraint, the I and the j has to be different, and I also have to leave out the i's and j's that are equal to 1. This means, this backslash means not include, right? So it's the set A without including the 1, okay? So, and there are particular ways of writing that up in CPLEX. All right, so everybody okay with the formulation? Yes? I need some interaction, some feedback, so feel free to speak up, all right? And stop me if you need further explanation or something. All right, so we're gonna make a new project, and I'm gonna create it with a model and a data. Okay. So let's define first the problem size. And I'm gonna say that problem size is gonna be defined by n, and I'm gonna define it in the, wait, what am I missing here? Anybody? Why is there an error there? What? I have to say, yeah, I have to declare which kind of variable it is, right? And which kind of variable is this one? Integer. All right. So those 3 dots means that I'm gonna be assigning a value to this variable from the data file. So if I go to the data file, I just write, we're gonna start small with a size of 5. Okay, that's in the data. And it's the only thing we're gonna write in the data. Okay, so all right, so we don't have, I'm not providing, intentionally I'm not providing any data information about the city. So what we're gonna do is we're gonna test how long it takes to solve the travel assessment problem. As you know, there is a problem in NPR, so the solving time grows exponentially with the size of the problem. Okay, so big instances is going to take way too much time, and we're going to try to see how that changes here with the size of the problem. So we're going to be generating random data, and then we're going to be changing the size of the problem to see how the time changes with the size of the problem. So let's start with the generation of the random data. Okay, so first I'm going to generate random locations, and I need to store those locations. And I'm going to be representing the location with a set of coordinates. So I'm going to generate random coordinates. All right, so I'm going to use this type of variable, the location one, to store the coordinates of the cities that I'm going to have. And I created the type of variable age that is going to represent the link between two cities, okay, from I to J, any two cities. And I'm missing something. So the cities are going to go from 1 till n, all right? I'm going to create the set of edges now. I'm going to create all of the links possible. So I'm going to create a set of, and this is the inside I have to put the type of variable, and I just created that type of variable, so it's going to be creating a set of edges. And I'm going to name it, I'm just going to take the plural edges. Edges is going to be defined as a set All right. Here I'm creating all of the links possible. So it's every pair of I and J among all of the cities, excluding the I and J's that are equal. Okay. This here means different. This is how you write different in or not equal. This is how you write not equal. So all pairs I and J that are in cities, remember that city goes from 1 to n, such that I is different than J, right? And now I'm going to create the cost. Remember that in the problem, the cost is ij, so the cost is defined for a link, right? So this is going to be defined over all edges. So I don't need to define it as a matrix with two dimensions, cities and cities. So since I define edges, I'm gonna define everything over that. and it's just an array with one dimension, just that dimension has a tuple, and that has both ends of every edge, okay? And to store the location of the cities, so in this array, I'm gonna in this array, I'm gonna store all of the coordinates of the cities, okay? All right. And now we're gonna do some pre-processing, okay? Pre-processing is just tell CPLEX that to do something before solving the problem. Last week we saw post-processing, doing something after you solve the problem, okay? We're gonna do both, but first the pre-processing. Pre-processing. So random locations first. So for every city, okay, so I need to generate a random x coordinate, and we're gonna use the function from OPL, rand. All right, so we're gonna be using a square, 100 in the x-axis and 100 on the y-axis, so it's a square. So the 100 there means that it's going to generate random numbers between 0 and 100. These particular functions gives you integer numbers, all right? So it's going to generate integer numbers between 0 and 1. I mean 0 and 100. And the same thing goes for the y location. Okay, so I need first the location of the cities so I can calculate the distance between them. So that's how we're gonna have the cost. The cost is gonna, in this case, gonna represent the distance between all cities. So in order to get the distance between two cities, I'm gonna define a function that is gonna calculate distance between two cities. So of course, to calculate the distance, I need two cities. So I'm going to define a function of city 1 and city 2 that is going to return the distance between those two. So it's going to return, everybody knows the formula to get the distance between 2 points, right? The square root, blah, blah, blah. All right. So I'm just going to write it. That's the square root. Okay, so it's city 1 x minus city 2 x, right? And this to the power of 2 plus the same thing All right? Agreed? So let's now store all of the distances. So for every edge and the set edges, that's all right. So um, so city location contains uh, well, all of the locations of the cities, and the index is the integer number that represents a city. So here with the for loop, I'm going through all of the edges. So for for a particular edge, I can by using this statement, I can find out which city is the first one in the link and the second one. Remember, each edge has an I and a J. So here I'm calling the first city in the link, and with E.J I'm calling the second city in the link. So city locations has the X and Y of every city. So here, what is highlighted there represent the location, they represent the X, Y of city J in the edge E. All right? So that's the second city and the first city there. So then the function gets the city and then calls the coordinate X and the coordinate Y of each one. And that for all of the edges. Cool? Agree? Okay, so far here we already generated all of the random data. So let's now create the model. So we talked about xij being a binary decision variable. So binary here is represented by Boolean. With that, we're saying that that corresponds to a binary variable. So Boolean, we're gonna call it x, and that is gonna be defined for each of the edges. And the other variable that was on the model is u here. This is like a dummy variable, and so by this formulation, the only thing that you can say from here is that that's a continuous variable, and we're just gonna say that it's positive. Okay. If you look at here, the u is never gonna be for city1. U is gonna, I mean, if you look at the constraint, the constraint, you're gonna see that the use goes from city2 to city n. All right. So there's no need to create the u for city1. Okay. So I'm just gonna create from 2 to n, and you can just do this. Okay, so and I'm creating an expression now that's going to represent the total distance. So it's going to be a summation over all edges. This is exactly as writing here the double summation over i's and j's, but this is just shorter to write. Right, so the problem would be minimize total distance subject to all right, so first thing you gotta see here is that is over all j's in A representing the set of cities. So for all j's in cities, if you look at this constraint refers to the inflows, all the links going to J. So I'm gonna call this constraint, I'm gonna call it flow in. You can name it whatever you want. All right, so it's gonna be a summation of i's in cities, and I don't have to include the i's that are equal to the j, so such that I is different than j. And the x. Now remember that the x it's not defined as a matrix. You cannot write this because we define it that we said that the index of the x variable is going to be the edges, which is a tuple. So this is wrong. Instead, we're going to write a tuple there. Okay? And this got to be equal to 1. Clear? Good? No? Anybody? All right. You can always go back and see the video. So just going to continue. Now i's in series such that j is different than I. This is going to be flow out. It's going to be summations over j's in series. What am I doing wrong? There. J's different than I. All right, so the last one. All right, so look at this. This is for all i's and a excluding 1, and j's and a excluding 1, and I has to be different than j. So we gotta write all that in the for all. For all. So i's in series such that I has to be greater than 1, right? J is in series such that j has to be greater than 1, and j is different than I. All right? I is in series, I bigger than 1. J is in series, j bigger than 1, and different than I. So this is for the subtour elimination. All right. Good. Let's see if it works. So in run configuration, you would create a new configuration there, and we're going to be using the model and this data. Right click, run this, and did it work? Right, so the solution is optimal. The objective function is 236 that you can see down here. Total distance 236. If you go to the x variable, just click there, and you have here the result. If you sort it out, these are the variables that are 1. So the optimal tour goes from 1 to 3, then to 4, then to 5, from 5 to 2, and then for 2 to 1 again. Right? And there's no subtour in the solution. Cool? Now I want you to see what happened when this grows. I'm gonna put a 500 there and run it again. Maybe that was too big. So right now it's not showing anything because it's still on the pre-processing, creating the random data. And definitely this was too big. Okay, there it is. So now started to solve right now it's not even solving it, it's trying to reduce the size of the problem. So CPLEX has like several heuristic and procedures that apply before actually solving the problem. So CPLEX reduces to the minimum size possible so that you get to the optimal solution faster. And now it started the branch and bound procedure. You can see there is no best integer yet. And this is the best bound. So far, I mean, you should know what the best bound is by now, right? So if you go here in the statistic, okay, I'm gonna change the size of the problem. This is too big. It's not gonna. So where is it? Okay, so let's put 100. All right, so there it is. The best bound is improving. I mean, and this is a minimization problem. So the best bound is going to start from below, try to go up. And there, CPLEX found the first integer solution at the top. So that would be the incumbent. And then I found another one. So what CPLEX trying to do now is get the lower bound as high as possible, so that it proves. I mean, if you get the lower bound to be equal to an integer solution, then you know that that's the optimal solution, and then CPLEX stops. So this is how it looks in the graph, and in the ingent log, you see the detail. So you have here, every now and then, it tells you how long it's been so far. It gives you, this is the best bound. No, excuse me. This is the best integer, and this is the lower bound. So far the gap, the relative gap between the optimal, I mean, between the lower bound and the incumbent is 25%. All right, so it takes a long time, right? I'm just gonna. Okay, so that one is working faster. Okay. All right. So there it is. See the lower bound getting closer and closer. All right. So have you gone over what the node selection strategy is, branching direction, stuff like that? No? All right. All right, fine. You can play afterwards at your place and just see how long it takes. So, I mean, as you realize now, different sites take different time, right? Okay. And it may look like 100 or like a 50. It's not big, but I mean, look at how long it's been. And this is an easy problem because the edges are symmetric. So going from I to j is the same from j to I. And also there's Euclidean distance. I don't know, like everything matters and mixed integer programming. So it depends on the problem. All right, so fine. So let's say now that you wanna try out different sides of the problem, and you want CPLEX to tell you different sizes, different time, and what is the objective for each one. All right. So instead of you waiting for CPLEX and changing the size every time, we're gonna write a procedure which is gonna change the side of the problem and run it one after the other and print the statistic that you wanna have. All right. So, and that's called what was the name of that? Flow control. That's called flow control. When you don't write anything in the flow control, it just CPLEX take over the control of the problem and it solves it. All right. So it goes over first through the pre-processing, then the model, and then the post-processing. There, it finished. That's how it looks. All right. Okay, so now you believe what Dr. Sud is teaching, right? Okay, so we go to the model and the flow control. Or the flow control, yes. The flow control. So we're gonna, instead of execute, we've been writing execute so far. So whenever you write main, you're gonna start taking control over how CPLEX is gonna go through your problem. So there are certain things. First, you have to have variables to represent the model as well. I mean, here you're taking control over everything. So so mod is going to be the variable representing the model. And we're going to refer to it as OBL. There. Okay, so this variable has the model, like the variables, the constraints, all that. And we need a variable that is going to represent the data of the model. All right, so I'm going to create a for loop and where I'm going to be changing the size. I'm going to start with size 5. And while the size up to, say, 50. I'm going to try size from 5 to 50. And I'm going to be saying that I want a step size of 5. So here I'm going to be trying out size from 5, then 10, 15, 20, 25, until 50, right? All right, let's see what this means. So every time I change the size, I have to create a new model which contains that size, all right? Uh, so last week we talked about CPLEX being different than CPLEX Optimization Studio, right? That CPLEX actually is the engine and you don't ever see it, right? And you write a problem, but that's not CPLEX, it's just OPL and it's just the code. So what I'm doing here is that I'm creating a new instance of the CPLEX engine that I'm going to be using to solve my model. So, so I create a model, and what I'm going to, so I create a new model, which is going to be solved with this new instance of the CPLEX engine, and with the model definition that here that I'm making difference. I mean that I'm making reference of up here, which we know is the current model. All right, so using this model definition plus this new instance of the CPLEX engine, create a new model. And that is actually going to be, that's the thing that's going to be solved. Because this new model contains both the CPLEX engine and your model definition. Here's when I'm taking the new, here's when I'm changing the new size. I mean, I'm changing the size of the problem. And it's defined in the data file, right? We have the model file and the data file. And the data file, I mean, here is n with this value of 50. So now in the flow control, I'm taking over that and just allocating a new number, which is going to be the size that's going to be changing. And I'm going to take my new model, and I need to add this new data. So the data source that I'm going to be using is that one, the one that I just modified. So to this new model, in which there's the model definition and plus the CPLEX engine, I'm now adding the data, which has the modified n. That's all it has. So now I need to all right, so every time you change the data of a model, you have to generate. Every time you assign a new data source, you have to include this statement. Have to include. So that it generates, again, the model. I mean, so that it generates the model with the model definition plus the data that you provided. So otherwise, it wouldn't know. I mean, it's not going to be like constructed. It's not going to work, all right? So you have to generate the model with both the data and the model definition. And finally, you have to solve it. So all right. Okay, so here I'm doing two things at the same time. When you tell the CPLEX engine to solve the model, CPLEX is going to give you a true or a false, meaning a solution was found or not. So you can do two things at the same time in only one statement here. So when the ghost gets to this statement here, it's going to do if CPLEX solve. So what it's going to do first is going to solve and then use the answer to know whether it was solved or not, all right? So we don't have to write different stuff. We choose just one line to write up that. So if it was solved, I wanted to write some statistics. You can play with anything here, but we're gonna be writing just. All right, so this is gonna be just one line. You're gonna see it as only one line. There's something wrong here. Okay, so this part is important. After you use the objects, you have to close them. If you don't close them, they're gonna stay open and they're gonna use memory of the computer, right? I mean, you've seen as this is a small problem and it still takes a lot of time and it uses a lot of memory. So if you're actually with a real problem, you're not careful and like deleting objects that you're not using any longer, then it's gonna use a lot of memory and you're not gonna be able to run your program. So let's see if this works. So there is two. Looks crazy. Yes, the reason is it's solving one problem after the other. That's why it's going up and down. If you go to the engine log, to the scripting log, while it's running. my God, it's so slow. All right. So far it's solved the problem with size 5 in less than a second, also with size 10 and 15. With 20, took almost 2 seconds. Look at the difference here. When you go from 20 to 25, now it takes 10 seconds. That doesn't look a lot, but if you look at the difference, you just went another 5 again. But instead of going from 1 second to 2 seconds, you went up to 10 seconds. So this is what teachers mean by saying that the problem is simply hard. Is that as you grow the problem, the time that it requires to solve it grows exponentially. And this is what exponentially means. I mean, this is only these problems is 8 times the first one, and it doesn't take 8 times longer. It takes way longer. It takes way longer to solve it. It's not just 9 times. And then it's going to continue until it gets to the size 50. That's going to take a long time, and that's going to be the last entry here. Questions? Yeah, we are just in time. Yes. Yes. Yeah, we haven't specified any special technique, so everything applied is gonna CPLEX is deciding whether it's better to use best no first step or like a combination, and also it runs some heuristic. It's not just branch and bound; it's another other heuristic also cutting planes in between, like everything. And you can go into details and specify whatever configuration you want to use specifically. I'm just going to show you where that is real quick. So a convenient thing, if you're going to go into a specific on how CPLEX is going to solve here, and the problem, you need to create, where is it? Setting. You create a new setting, all right? So we're going to call in. So this setting, and you need to put it in the configuration run that you want to use. So you are able to create different settings and use it on different configurations. If you want to try out different configurations, I recommend always creating different run configurations so you don't forget what you did previously. All right. All right. So once you got it inside the configuration, for example, for mixed integer program, these are all the things that you can do. The general, if you actually want CPLEX to like display information in the engine log, strategies. This is interesting. Here you choose branching direction, whether it goes up or down whenever it's going to branch in a variable. Where's the other one? Node selection. Right now, by default, uses best bound. You can choose depth first. With depth first, it's going to use less memory, but it's going to take longer. What else? Priority. Well, you can play with this. There's also memory. There's limits here. This is relevant. So, where is it? Where is it? Oh. All right, so this. Okay. All right, so this is the time limits. And where's the other one? And this is for the gap. You can stop the branch and bound before getting to the optimal. Sometimes getting the lower bound to the point in which it matches the integer solution, the incumbent, it takes way too long. So you can say like, okay, a 5% gap is enough for me. So you just here, you would write here 0.05 in this one here, relative MIP gap tolerance, right? Now, if you know the scale of your objective function and say like, I mean, if you want to minimize, and if it's under 1,000, you're fine with it. And the absolute MIP gap tolerance, you just put 1,000. And whenever CPLEX gets to 1,000, it's going to finish the branch and bound and not keep looking for solutions, right? So that's how you play with that. And one thing that I forgot to tell you before, guys, you know how you're modifying your model, and sometimes you want to remember what you did before, and you don't remember, and you want to compare your model with some other model also. There's this feature here. You right-click on your model and go to compare with, and in this case, I'm gonna compare it with a previously saved, the same file, but the version that was saved before. So when it was 11 a.m., I didn't have the flow control. So when you compare those two models, you're gonna see here that CPLEX is pointing out the fact that I didn't have all of this code before. So this is the new, the current one, and this is the old one, and it's pointing out the difference. And there's no other difference there, right? So this is how you compare two models too. You compare it with the history, or you can compare with some other different file. This is also useful. And all right, so I believe I covered everything that I wanted. So that's it. So next week we're gonna start with Java. I'm gonna post, or like we're gonna send an email, like with a small code that you have to run on your computer, just to make sure that everything is okay. If you're able to run that small code we're gonna send out, it means that you have CPLEX correctly, Java, and the reference you have to like configure just fine. And if it's not working, we're also gonna post like instruction on how to make sure that Java runs properly. You have that small code to make sure that it does. So you're prepared for the next class. That's it. Thank you.